instantaneous rate of change. So far, we've looked at a couple different types of rates of change, and we said that part of the reason that we want to study change is that we want to be able to use functions to predict what might happen at a later time. So far, we've looked at the relative rate of change and the average rate of change. So we're going to build upon what we know about the average rate of change to figure out what's called the instantaneous rate of change. So let's review what we know about the average rate of change. So the average rate of change tells us how much a function changes on average between 2 points. We look at the slope of the secant line and we use the formula f of b minus f of a over b minus a. When we do this, we're always looking between 2 points, and the result we get is something that's happening on average. What we want to do is we want to use this average rate of change to tell us about what's called the instantaneous rate of change. So the instantaneous rate of change is how much a function changes at 1 point. This is really powerful because if we can find out how much a function changes at 1 point, we can look at cumulative points to find out exactly how much a function changes on an interval instead of the average. We calculate the instantaneous rate of change by finding the limit of average rates of change of f of x over smaller and smaller intervals around a point A. So what that means is we want to look at a specific point that we're interested in. We're going to look at the average rate of change near that point, and we're going to see what the average rates of change are approaching as we get closer and closer to A. So we're going to look at some visual representations of this, but before we do, let's try to imagine what the difference is between average rate of change and instantaneous rate of change. A good example of this is driving your car. So consider that it takes you 3 hours to travel 150 miles to your cousin's house while you drive. Your average rate of change would be 50 miles per hour. Because if we look at the per hour travel, we went 150 miles over 3 hours. That's how much you changed on average. Now, your instantaneous rate of change is going to be the speed that you're going at any given moment. So if you're driving to your cousin's house and you look down at your odometer and it says you're going 75 miles per hour, that's your instantaneous rate of change because at that moment, that is how quickly your position is changing. So instantaneous rate of change is really what's happening at one particular moment. And we're going to use average rates of change to be able to calculate or to get a good approximation of this instantaneous rate of change. This is a method we use a lot in mathematics where we use something we know to try to figure out something we don't know. So we're going to start with a visual representation of this average rates of change to approximate instantaneous rates of change. So the example that we're going to use to motivate and visualize what's happening is the function 0.5x squared, which is the blue graph given below. Now, in this particular example, we want to try to approximate the instantaneous rate of change at -1. So at -1, we want to know exactly how much the function is changing. So what we're going to do is we're going to look at average rates of change near -1 to help us approximate. And this is how this works. So we're going to approximate the average rate of change to the left of -1 and to the right of -1. So when we do this to the left, I'm looking between the points -1 and -2. So I'm going 1 unit to the left. And when I approximate the average rate of change, I'm going to do f of b minus f of a over b minus a. So here, I'm going to be doing f of -1 minus f of -2 divided by -1 minus -2. Be careful with your negatives here. So for this particular function, when I plug in a -1 into my function, I'm going to get 0.5 minus, and if I plug the -2 into my function, I'm going to get 2 divided by, now negative 1 minus negative 2. The minus and the negative are going to cancel, and I'm going to be left with a 1 on the bottom. So crunching that number is going to give me negative 1.5. So the slope of this line, the average rate of change between negative 2 and negative 1, is negative 1.5. And again, just for reference, when I calculated f of negative 1, I took negative 1 and I plugged it into the function to get the y value of 0.5. Now, I'm going to do the same thing, but I'm going to do it to the right of negative 1. So here again, I did the left in red. So now I'm going to do to the right of negative 1 in green, so we can see what the slope of that line is going to look like, again, using average rates of change. So to the right, I'm using the point 0 and x equals negative 1. So I'm going to do f of 0 minus f of negative 1 divided by 0 minus negative 1. So f of b minus f of a over b minus a. Now, it's not a coincidence that I went 1 unit to the left of negative 1 and 1 unit to the right of negative 1. I want to be consistent in how close I am to negative 1. So since I went 1 unit to go to negative 2, I also went 1 unit to go back to 0. So plugging these numbers in, f of 0, if I plug 0 into my function, is going to give me 0, minus f of negative 1 is 0.5, divided by, now on the bottom, the negative and the minus are going to cancel out. So divided by 1 gives me negative 0.5. So the slope of the line between negative 1 and 0 is negative 0.5. So what does that tell me about how much the function is changing at negative 1? So what that tells me is that my instantaneous rate of change, which is what I'm looking for here, has to be between negative 1.5 and negative 0.5. This is going to give me bounds as to where my instantaneous rate of change needs to be. So we can see that there's about a 1 unit difference between negative 1.5 and negative 0.5. So what we do, as we said before in our definition, is we want to take the limit of these average rates of change as we get closer and closer to negative 1, or as we get smaller and smaller intervals around negative 1. So if we want to get smaller and smaller intervals, we want to repeat this, but now instead of going 1 unit away from negative 1 in either direction, we want to stay a little bit closer. So let's look at the next picture here. So now we have the same function, 0.5x squared, but now when we look to the left and the right, instead of going 1 unit away, we're going to go 0.5 units away. So we're getting closer to negative 1. So when we do the average rate of change to the left, we're going to be using the point negative 1 and negative 1.5. So we're going to do f of negative 1 minus f of negative 1.5 divided by negative 1 minus negative 1.5. So again, we're finding the slope of the red secant line. We're doing this rate of change to find what's going on here. So we said f of negative 1, we're going to plug in again to the function here, is going to give us 0.5 minus 1.125 divided by, now on the bottom we have negative 1 minus negative 1.5. Again, the minus and the negative are going to cancel, and that's going to give us 0.5 on the bottom. When we plug that into our calculator, we get negative 1.25 for our slope of the average rate of change to the left of negative 1. The slope of that secant line is negative 1.25. Again, we also want to calculate the average rate of change to the right of that point. And when we do it to the right, we're also going to go 0.5 units. So now we're going to do f of negative 0.5 minus f of negative 1 divided by negative 0.5 minus negative 1. So again, we're going to take these numbers and we're going to plug them into our function. When we plug in negative 0.5 into our function, we're going to get 0.125. So 0.125 minus, when we plug in a negative 1, we get 0.5 divided by, now again on the bottom we have minus and negative, so those are going to cancel. So we're going to divide by 0.5. When we crunch that number in the calculator, we get negative 0.75 as the slope to the right of negative 1. Now, in the last example, when we were 1 unit away, we were 1 unit apart in terms of where our interval was. So we can see that our interval is a little bit smaller because now our instantaneous rate of change has to be between negative 1.25 and negative 0.75, which is only a 0.5 interval length. Before it was a 1 unit interval length. So the closer we get to negative 1 with our approximation, the smaller our interval is where our instantaneous rate of change needs to live. Turns out, if we get closer and closer and closer, eventually the average rate of change on the left is the same as the average rate of change on the right. And when that happens, the slopes of those two lines are the same and they become one line. If we were to do that with this particular example, what would happen would look like this. So the average rate of change on the left would approach negative 1, and the average rate of change on the right is approaching negative 1, and eventually they both reach negative 1. So that means we have one line now, and it has a slope of negative 1. And that one line touches at the one point that we were interested in, right here at negative 1. And so we know then that the instantaneous rate of change has to be negative 1 because that's what both sides approached as we get closer and closer to negative 1. Turns out that this line has a special name and has special meaning. Remember that the slope of the secant line, which was a line that connected 2 points, was our average rate of change. This line is called the tangent line. The tangent line is a line that touches a function at a given point, so at one point. The slope of the tangent line is the instantaneous rate of change at that point. So again, we used secant lines, which gave us the average rate of change, and eventually they became one line, which we then call the tangent line. So one of the main differences here is that secant lines connect 2 points. Tangent lines touch at 1 point. Both of them, however, we evaluate the slope to tell us how much the function is changing. The slope of the secant line gives us the average rate of change, and the slope of the tangent line is going to give us the instantaneous rate of change. So let's take a look at how we can use what we just learned from the graph about instantaneous rate of change to talk about how we might do this on a table. Now, tables are really important because most of the time in the sciences, when you're evaluating what's happening with functions, it's based on data that you've collected. So in physics, biology, chemistry, a lot of times there are experiments and you're charting the different values that you have. So you don't actually have a function that models the whole thing, but instead you have various points that you want to use to make some calculations and assumptions about. So we're going to look at some tables and we're going to look at how we can apply what we've just learned to find and approximate instantaneous rates of change. So remember, our goal is to look at the average rate of change near the point to help us make decisions about what we think the instantaneous rate of change is going to be. So consider that I've thrown a tennis ball up into the air and I have the ability to measure the height of the ball, called S of t, in feet, for time t in seconds, and I've recorded the data in the table below. So I'm interested in trying to approximate how fast the ball is traveling when time equals 1 second. So the way I read the table before I've done any analysis on it is that time equals 0, the ball is 6 feet in the air. So if you imagine a person standing up and they're throwing a ball up in the air, when they let go, their hand is probably about 6 feet off the ground. So that makes sense. After 1 second, the ball has reached 9 feet in the air. After 2 seconds, it's 11 feet in the air. After 3 seconds, it's 12 feet in the air. But then at 4 seconds, it's 10 feet in the air. So it started coming back down. So that's what's happening if you're trying to visualize. But I want to know, how fast is that ball moving at time equals 1? Now, because I don't have the actual function that models this situation, and I just have some points, that means that I'm going to be doing an approximation. So I'm going to get my best guess mathematically at how fast that ball is moving, while keeping in mind that if I had the actual function, I'd be able to get better information. So again, our goal is to look at the average rate of change near the point I'm interested in. So I'm interested in what's happening at time equals 1. So what I'm going to do is I'm going to calculate the average rate of change to the left of my point and the average rate of change to the right of my point, just like I did on the graph. And I'm going to use the closest point that I have because that's the most accurate data for what I'm looking at. So let's start by finding the average rate of change to the left of 1. So when I say to the left, that means I'm going to be using the information at 1 and the point directly to the left of it. So again, I'm going to apply this to my average rate of change formula. So I'm going to do f of 1 minus f of 0 over 1 minus 0. So f of 1 means I'm going to go to my table and find the dependent value. So I have 9 minus, now f of 0 is going to be 6 divided by 1. So this is going to be 3. So remember that sometimes we can attach units if we're given them in the problem. So this 9 and this 6 on the top, these are both dependent values. So that's in feet. And then on the bottom, the 1 minus 0, the units on that is seconds. So this is 3 feet per second. So my average rate of change between 0 and 1, which is to the left of 1, is 3 feet per second. I'm also interested in looking at the average rate of change to the right of 1, just like we did on our graph, because we want to look at smaller and smaller intervals around 1 on both sides. So to the right, I'm going to be looking between 1 and 2. So I'm going to do f of 2 minus f of 1 divided by 2 minus 1. So that's going to be 11 minus 9 divided by 1. And that's going to give me 2 feet per second. So my average rate of change to the right is 2 feet per second. Now, because I have a table, I can't make this information any better. I don't have a way to get closer and closer like I did with the graph, because with the graph, I had the function and I could just keep plugging things in. But here, unfortunately, I don't have a good way to do that. So my left hand approximation was 3 feet per second. My right hand approximation is 2 feet per second. Since I can't make that any better, my best guess is going to be to average these two numbers together. So that means I'm going to add 3 plus 2 and then divide by 2. So my best guess for the instantaneous rate of change is 2.5 feet per second. So again, this is an approximation. This isn't an exact. So when I write about this and I talk about the instantaneous rate of change, I'm going to be using the approximation symbol. But it is a fairly good guess because I know I have to be between 3 and 2, and there's not too much variability between there. Now, a note about the units. So again, we get the units of the average rate of change because we're taking the dependent units, which were on the top of our formula, divided by our independent units, which were on the bottom of the formula. Since we're using the average rate of change to approximate the instantaneous rate of change, the units of the instantaneous rate of change are also going to be in feet per second. So again, you can take the average rate of change units, and those are going to be the same as the instantaneous rate of change units because we're using the average rate of change to get to the instantaneous rate of change. Now again, not every problem is going to have units, but when they do, you should go ahead and start using them because they're going to become more and more prevalent as we go. Now, just like on the graph, If we were able to get closer to 1, our approximation would be a bit better because our bounds wouldn't be so far apart. So let's take this example and let's extend it a little bit to see how this might work on a table. So now let's consider that during our experiment, someone with better tools than I have was also measuring the height of my ball. In fact, they were able to measure every half a second. So now my table has more data. Notice that at 0, 1, 2, 3, and 4, that those positions are the same. The position didn't change. What happened here is that I now have more information about where my ball was at 0.5, 1.5, 2.5, and 3.5. So the numbers you see in red are additional information than what I had before. However, what I had before didn't change. So now, when we want to try to figure out how quickly my ball was moving at time equals 1, I have closer information. So let's see what kind of impact that has on my calculation. So again, we're going to look at what happens when we take the average rate of change to the left and the average rate of change to the right. So what's going to happen here when I take my average rate of change to the left is that I'm now going to use the 1 and the 0.5 because the 0.5 is the closest point on the left of 1. So I'm going to do f of 1 minus f of 0.5 divided by 1 minus 0.5. So again, on the top, that means I'm going to do 9 minus 7.8 divided by, now on the bottom, 1 minus 0.5 is 0.5. So 9 minus 7.8 is 1.2 divided by 0.5 is going to give me 2.4 feet per second. So again, the units are going to be feet per second for the same reasons that we had above, because the dependent variable is in feet and time, which is in the bottom, is in seconds. Similarly, we're going to calculate the average rate of change to the right of 1 using the closest point to the right, which is now the 1.5. So we're going to have f of 1.5 minus f of 1 divided by 1.5 minus 1. So that's going to give me 10.1 minus 9 divided by 0.5. So that's going to give me 1.1 divided by 0.5. And when I put that in my calculator, I'm going to get 2.2 feet per second. So here we can see that by getting closer to 1, our approximation has become much, much better. So now we know that the instantaneous rate of change, or the speed at which my ball is going up into the air, has to be between 2.2 feet per second and 2.4 feet per second. That's pretty close. Again, my best guess would be to average these two numbers together, which would give me 2.3 feet per second. So without any further information, I would make an approximation of 2.3 feet per second. And again, that's only if I can't make it any better. But let's see what happens if I can make it just a little bit better. So finally, let's consider that during our experiment, someone who has the best measuring tools was also measuring the height of my ball, and they were able to measure every 1/100th of a second. So almost at every single moment in time. So again, I could fill in the data for every 1/100th of a second, but that would make the table really, really big. So instead, I'm zooming in on what the data points around 1 would look like if I had measured every 1/100th of a second. So here, again, I want to do an average rate of change to the left of 1 and an average rate of change to the right of 1. And if we're going every 1/100th of a second, that's going to be really, really close. So when I do the average rate of change to the left, I'm going to do f of 1 minus f of 0.99 divided by 1 minus 0.99. Now when I put this into my calculator, there's a lot of decimals. So I saved all the decimals and crunched them all at once. And when I put it all in, I got 2.3645. So that was the exact number I got. I didn't round that. Now, When I do the average rate of change to the right, I'm going to be doing f of 1.01 minus f of 1 divided by 1.01 minus 1. And again, I took these decimals and I crunched them in my calculator very, very carefully. And I got 2.3645. So what's happened here is we got so close to 1 that we got close enough that we don't even have to make a best guess anymore, because the average rate of change on the left became the same as the average rate of change on the right, which means that that is the exact instantaneous rate of change. So my instantaneous rate of change here is 2.3645 feet per second. So again, if the average rate of change on the left is the same as the average rate of change on the right, you've gotten to the point where the lines are the same and you have that tangent line. And the slope of that tangent line is 2.6345. So at time equals 1, at the 1 second mark, that's how quickly my ball was moving in space. And again, that's telling us the change of the function at that point. And change always tells us how much the dependent variable changes for every 1 unit that you move in the independent direction. So that means that at this particular moment, that if I were to move 1 second into the future, that my ball would go up 2.3645 feet. So 1 unit in the independent direction, which was time, would result in a 2.3645 increase in the dependent direction, which is the height of the ball. So I was able to get the exact instantaneous rate of change. Now, let's summarize the important points here about instantaneous rate of change. The instantaneous rate of change is how much a function is changing at 1 point. And the way we get the instantaneous rate of change is by looking at average rates of change around the point we're interested in, and we want to get as close as possible. Sometimes we can't get that close, and if that happens, we have to use our best guess by averaging the average rate of change on the left and the average rate of change on the right. However, if we are able to get closer, we're able to shrink the interval and make a better guess about what our instantaneous rate of change will be. The instantaneous rate of change is the slope of the tangent line, if we are able to find it, for a function at a given point.